And hi everybody, welcome back to Quantum Mechanics, and this is lecture 14. We'll take a little review as to what we've done already. So as we know, our rules of quantum mechanics tell us that first of all we need to describe the system using classical mechanics, and then we insert the quantum mechanical operators for the particular observables that we care about, usually momentum and position. Then we build the Schrodinger equation, then we solve the Schrodinger equation, then we apply some boundary conditions. So as a review of what we've just covered in lecture 13, so this is lecture 14, what we covered in lecture 13, we looked at Hooke's law, we looked at Newton's second law, F equals ma, and we looked at how we measure the potential, and the potential energy is an integral of the force with respect to position. So we see this again, potential energy is a function of position, and so we find this with conservative systems. We talked about harmonic oscillators, we talked about little boys or girls on a swing, moving backwards and forwards. We put forward an equation that described these conservative systems, and the solution to this particular equation is a wave equation. Okay, and we tied that in with simple harmonic motion that you would find from a mechanics or physics course. So again, the classical description here is required before we go quantum. It's the plan today is to go quantum. What's our application? We're going to be thinking about diatomic molecules. We're going to be thinking this is a chemistry course after all, so we have to think about what those molecules consist of. We'll start with very simple diatomic molecules. We recognized in lecture 13 that we have a single reduced mass, so we can replace the mass in sort of single ball on a spring problem. We can replace that with the reduced mass when we have two atoms that are connected and vibrating. And the reduced mass, well, the position of that reduced mass is found at the center of mass for that molecule. So that's a review. Let's look at what we're going to cover in today's lecture. So we're going to talk first about the internuclear potential. It's called the Morse function, and we're going to again consider the harmonic oscillator. We're going to ask ourselves, what would the Hamiltonian operator look like for this system now that we know what it is classically. I'm going to provide solutions for you for the energy. We're going to find that solutions to this Schrodinger equation are beyond the scope of the class. So I'm going to provide these solutions for you, at least in terms of energy. We will also talk later in the lecture about the actual wave function. We're going to explore the Heisenberg uncertainty principle implications. Very interesting results for this simple harmonic oscillator and for this diatomic molecule. We're going to talk about something called selection rules. I'll introduce that when we get to it, but it basically tells us that we can only go up and down a single vibrational quantum number level in these diatomic molecules. We'll see how that ties in with spectroscopy. Okay, so I'm going to introduce some spectroscopy and plant some seeds. We're going to take a look at some mathematics, a review of power series. We're going to apply that to the potential energy for the diatom, for the diatom. We're going to talk about anharmonicity. So the anharmonicity is going to tie back to the graph I'll show you for internuclear potential. And I'll plant also these are all seeds, plant some seeds for perturbation theory, which will come later in the course. And then lastly, we'll talk about Hermite polynomials. So these are included in the solution for the wave function, and we'll look at that much later in the lecture. So thanks for joining me today, and let's kick on and take a look, therefore, at the internuclear potential for this diatomic system. So what we're going to do first is consider what we call the Morse potential. Okay, so this is the internuclear potential we're going to look at in here, or the Morse potential. And let's draw a graph as best as I can. So here are our axes, and on the y-axis we have potential energy, and on the x-axis we have internuclear separation. And so what this graph looks like, and I'll draw this again in red. I'm also going to draw another graph in here. I'm going to ask you to think about what that graph is. It's not difficult to, or it's quite difficult to figure it out from my drawing skills, but we're going to talk about these two graphs. But first, let's come back to the Morse potential, and we'll put a few things on this graph that will start to make sense for us. So this we're going to call the bond energy. And we're going to say, okay, let's remember this is our internuclear separation. So very large internuclear separations, that's really where we have these two atoms that are connected together. Very large internuclear separation, we've effectively broken the bond, right? So we're going to break the bond, and that would be when x is equal to infinity, or the internuclear separation is equal to infinity. And then we're also going to have what we're drawing here. This is supposed to be a curve at the bottom. It's actually going to be a quadratic at the bottom in here, but we're going to say that this position here is L0. And so I'm going to say that down in here, at least we expect something like a quadratic type curve at the bottom. And what we also find that is if we bring these atoms close together, so up here what we find is that if we push these atoms close together, what happens is the potential energy rapidly increases. So there's a lot of repulsion between the electrons, and the repulsion in particular with the nuclei in those two atoms. And so we very quickly ramp up. And there's a very steep incline, in fact, in this curve that I'm showing in here. So that's our Morse potential. Here is the red curve. So that's our Morse potential is the red curve. So what was the blue curve? The blue curve, let's actually write this in blue. So we've got to remember, of course, that V is equal to the integral of the force with respect to x. So that would be equal to, so remember from Hooke's law, our force ends up being equal to minus kx. And so what we'd end up with would be V is equal to kx squared over 2. So that's our potential. So we also recognize, by the way, that x, at least for our ball on a spring, we had an x being equal to L minus L0. So when we think about it, x squared, in fact, would be L minus L0 here squared, and so we plug this into here. And what we'd recognize here is that actually the blue curve is simply equal to y. This is what I'm trying to plot here, is y equals half k L minus L0 squared. And that's what that blue dotted line is supposed to be. And why do I bring this up? So it turns out that the blue curve is a good approximation for vibrations with small amplitudes. So small amplitudes means we're kind of oscillating backwards and forwards in around this region of L0, okay? And it turns out that there's this really good overlap in this region right in here. All right, so just in this region down here at the bottom of the curve, there's a very good overlap with the Morse potential that would be measured for a diatomic system, and a quadratic equation that is built on the harmonic oscillator that we just described classically. So this is where we say to ourselves the diatomic atom is similar enough to the harmonic oscillator so that we can build a Schrodinger equation for this diatomic system based on that classical description. So therefore, let's actually look at the Schrodinger equation here. What would our Schrodinger equation look like? So of course our Schrodinger equation, we all know this, right? But what we have to do, this is rule 3, is to build the Schrodinger equation. But what we have to do first of all is determine the Hamiltonian operator. So we've got, of course, our kinetic energy is equal to p squared over 2 mu. So now we're going to be working with this reduced mass, and the potential energy is equal to, well, we're calling that V. It's the same thing as potential energy, and so we just described that in the previous slide. That's equal to half kx squared, and we're also going to recognize now for this total energy of the system, so the Hamiltonian operator is going to be the kinetic energy operator plus the potential energy operator. And so what we have to do now is plug in our quantum mechanical operators, and the kinetic energy is kind of easy. We've done that before, so the kinetic energy is simply going to be, well, remember, our momentum operator is equal to minus I h bar di by dx. So we're going to work in the x direction right now. So we square that term and we end up getting minus h bar squared over 2 mu di squared by dx squared. And potential energy operator is therefore, well, the potential energy operator has this x, it has the position observable in it. So our position operator, so we can look that up, and it's simply multiplied by x. So it's actually straightforward. The potential energy operator is now going to be equal to half kx squared. It's very simple. So now we're going to build that together, or add these two together. So these two become the Hamiltonian operator, and that Hamiltonian operator we plug into our Schrodinger equation. So let's look at the result. It's minus h bar squared over 2 mu, and I've just added the wave function here, psi as a function of x, anticipating, right? So here's our wave function. We have to build the Schrodinger equation, so we include that wave function. And remember, this operator that we have in here is going to operate also on that wave function. So this is how and why we build up our Schrodinger equation for this harmonic oscillator. What we now do, let's multiply throughout by minus 2 mu over h bar squared. So we multiply the whole equation, and we're going to end up with a new expression down here. Oh, let's try some green, and our final equation is so here's our final equation. Here's our final Schrodinger equation. Here are the limits. So we have to consider that we can stretch that molecule all the way to infinity, and we have an expression now with a 0 on the right hand side. And so let's think about how we might solve that particular Schrodinger equation. Well, the next slide kind of tells us, well, what I've done here is I repeat that equation from the previous slide, and I'm going to simply state at this point that the solution is very difficult to find. Why? Well, it turns out that this psi term in here, it does not have a constant coefficient. So the coefficient here includes a term associated with x squared, right? So it's not a constant coefficient. So this makes the solution of this problem, this eigenvalue problem, really difficult. And it can be found, and we'll think about how it's found later, but it is found by substituting a power series into the differential equation and then determining each coefficient sequentially. So we'll look at that in a little bit more detail later on. But basically this solution, I will say, is outside the scope of the course. What does that mean? Well, we basically talked about how when we were looking at the particle in a box, that solution was fairly difficult. And I said that really as we start to get to slightly more complicated systems, the mathematics gets quite hard. It turns out that when this was developed in the day, the mathematics for this was already developed. That mathematics was available before quantum mechanics came along, so the physicists of the time could borrow from all that mathematics that was already published. There is a second method beyond the power series method, an operator method, that's going to be found in chapter 5, your appendix. But I am going to give you the solution. So the solution I'm saying is figuring out that solution is outside the scope of the course. But what is the solution? So the solution, and I'm going to give you the solution for the energy, and we're going to call it E sub V. The V is the quantum number associated with the vibrations, but the solution for the energy here is E sub V equals H nu times V plus 1/2. It's important to know what these things are. V is the quantum number. So a quantum number, we'll later see this quantum number comes out of the solution, out of the mathematics. So that's important. We're also, there's this new term in here, and that's equal to 1 over 2 pi. And we've got the force constant K and the reduced mass in here. And that's the square root of that. So let's make sure we clarify what these things are. So the K is the force constant. The mu is the reduced mass, and the V is the vibrational quantum number. And we're also going to recognize now that this new term, this is going to be the fundamental frequency. We'll come back to that. So what we're going to do first is look at some key features of this solution. So remember, I've just told you that this solution exists. I haven't told you yet how we've figured it out, but it is the solution to the Schrodinger equation. It's the eigenvalue, right? It's this eigenvalue in here. So let's make sure that we know it's the eigenvalue and not the wave function yet. We'll come back to the wave function in a later slide. So what are the key features? Okay, I'm going to draw another graph in here now, and it's more or less the same graph. This is internuclear separation, and we're zooming in, if you will. We're zooming in on the bottom of that quadratic, and what we're going to find are that these energy levels are quantized. So we have a V quantum number, V equals 0, V equals 1 in here, V equals 2, V equals 3, and so on. So where does this come from? So again, these are the quantum numbers. Here's the solution. So basically the energy goes up gradually. As we increase the value of V in here, it goes up by a step that is H nu. So these steps in here are all the same. So we'll say that this is equal spacing. And we can start to write down some of these values. So for example, here we have E is equal to h nu over 2, and that's the situation where V equals 0. When V is equal to 1, we'll get E is equal to 3 over 2 h nu. So that's V equals 1. Again, let's just remember that equation. E sub V equals h nu V plus 1/2. So a couple of points to recognize here. So we'd also know that in a classical system, right, we know that when a little boy is sitting on a swing, okay, here's the little boy sitting on the swing. When he's just sitting there daydreaming and not swinging anywhere, we would say that the energy of that conservative system would be equal to 0, right? Because he's not moving. We've simply got there's no velocity, so half mv squared is his kinetic energy. That's equal to 0. He's not moving, and the potential energy, that potential energy kx squared over 2 is also 0 because he's in equilibrium position. So in a classical system, we know that we can have a 0 energy, no problem. The interesting thing here in quantum mechanics is that the lowest energy is called the 0 point energy, and this is the lowest energy. Right, it's when V is equal to 0. That 0 point energy actually means that we're not at a rest position. So we're not at this equilibrium position in here. So here's our equilibrium position. Okay, so at our lowest quantum mechanical energy, we find that we're actually still moving. We have some finite energy, and so there's a difference there between the quantum mechanical system and the classical system, and there's some importance here, and I'm going to basically say it comes down to the Heisenberg uncertainty principle. Because if we're at a position of 0 energy, then we know that the molecule is not moving at all. So we effectively know the potential energy of the system, and the potential energy of the system includes the quantum mechanical operator for position, but also we know that because it's not moving, the kinetic energy is 0. That would include the momentum quantum mechanical operator. And if we could know both the momentum, it'd be 0, and the position, it would be the equilibrium position, at the same time accurately, then that would violate this Heisenberg uncertainty principle. So it turns out that we're in a good position here. We're not violating the Heisenberg uncertainty principle. We can also think about the third law of thermodynamics, going back to our thermodynamics class. And we can think about that third law basically saying that entropy is 0 at the absolute 0 for a perfect crystal. And that basically is saying that nothing is moving. And it turns out that the quantum mechanics actually trumps the third law of thermodynamics, because we basically know at the absolute 0, every molecular system or crystal system must still have vibrating atoms, because we cannot violate the Heisenberg uncertainty principle. So quantum mechanics wins. Let me sum that up quickly and then we'll finish this little segment. So if the energy were 0, then both the expectation values of operator for momentum squared and
operator for position squared would have to be simultaneously, I'd say 0 in here, but I would also say precisely known. And this would violate the Heisenberg uncertainty principle, and we can't violate the Heisenberg uncertainty principle. So fortunately we're in good shape, because the lowest energy system we can have is with that diatomic molecule still moving. And that is this 0-point energy. Okay, next up we're going to think about what do these energies mean actually for us as spectroscopists. So we'll move on to that in the next segment. So this next section is titled Harmonic Oscillators and Infrared Spectra. It's section 5.6 from the textbook. And yes, we're starting to ask ourselves, what do these energies mean when we're doing infrared spectroscopy? So let me start by writing down the energy equation, so that the solution, the eigenvalue solution, so E sub V, where we're denoting that energy here is a function of the quantum number for vibration, that is V, and that is equal to h nu, that's the frequency of oscillation, multiplied by the v, little v inside the brackets here, that's the quantum number, plus 1/2. So v can take values of 0, 1, 2, etc., always integers. And we're first going to consider a situation where we go from v equals 1 all the way to v equals 2. So what would be the change in energy there? Well, that change in energy would simply be equal to h nu, and where v equals 2 initially, we got 2 plus 1/2 minus therefore h nu, and that would be 1 plus 1/2. So that's the v equals 1 is here, and v equals 2 is this term, and therefore we're left with, this ends up being equal to h nu, right? So everything cancels, and so what we're going to write down here, we're going to say that this is actually h nu obs, so that's the observed frequency. What else can we say? Well, it turns out, and later we're going to prove this, that delta V in here is always equal to plus or minus 1 for these vibrations. And how can it be that I can write this? This is something we're going to call a selection rule, and it comes out of the mathematics. So I'm planting a seed in here because we'll come back to this and prove this later. So this is really a seed, but this is an important seed. We often get a lot of selection rules in spectroscopy, and that's why we really only see single h nu positions in our infrared spectroscopy. So we're really, another thing we can say therefore for absorption spectroscopy, what we're going to say that delta E is always equal to E V plus 1 minus EV equals h nu, and that we can write down that obs subscript in here. We're also going to recognize this new obs term in here is equal to 1 over 2 pi multiplied by k over mu to the half, and that's in hertz. In principle for these diatomics, what do we typically see in our spectra? So when we actually start to measure absorption spectra, what we tend to see is that these, for diatomics, we find that nu obs is typically around 10 to the 14 hertz, and that's in the infrared. So many of you who've done infrared spectroscopy already will probably recognize that often the unit we use is wave numbers. So I'm going to also state now that it's customary to write down the following expression. G, also a function of V, and here's why it's a function of V, is equal to, so this is the frequency in wave numbers. Wave numbers, the units are centimeters to the -1. It's almost it's 1 over, it's like 1 over a wavelength in here. We'll come to that in a second, but this term is omega squiggle, I guess, and inside the brackets here, V plus a half. So where do we get this from? Well, this simply comes from this expression up here, but it's clearly been modified a little bit. But what we should recognize here, let's change colors again, is that E sub V over HC is what we are going to say is equal to this GV term. So what we're doing here is we're going to divide the EV expression. So what have we got? Our EV expression is EV equals H nu V plus 1/2. But in order to get the GV term, what we're going to do is divide this expression here by HC. And when we do that, the H's cancel, and we're left with this nu divided by the speed of light. A frequency times a wavelength is equal to the speed, and therefore, what do we have? We have frequency divided by speed is equal to 1 over the wavelength. That 1 over the wavelength term, when that wavelength is in centimeters, becomes our wave number, and so we end up getting this G of V term, and it's just customary to write this, and that is equal to the wave number times V plus 1/2. So a lot of fiddling around in there. What are the key pieces to think about? The key takeaway is this expression in here, and another key expression is the solution up here, and we're just tying everything together to spectroscopy. So let's look at an example in spectroscopy. So here's an example. We've got some molecule, hydrogen chloride, and we find that the observed wave number is 2.886 times 10 to the 3, and that's wave numbers. And the question might now be, what's the force constant? So this might be a question you might find on homework or on an exam. And so first of all, we're going to write down what that force constant is in terms of the expressions that we've seen already. So 2 pi c omega squiggle squared nu. Okay, so we can, it ends up being a plug and chug type exercise, and so that ends up now being equal to 2 pi times 2.998 times 10 to the 8 meters per second, multiplied by 2.886 times 10 to the 3rd wave numbers. All right, so that was our observed spectroscopic line, and then in here we have 100 centimeters per meter, because we're going to convert from centimeters into meters, and then we're going to square this whole thing, and we've obviously now got to multiply, and we've got to find out what our reduced mass is in here. So the reduced mass is, m1 m2 divided by m1 plus m2, so that's multiplied by, we're going to go with 35.0 atomic mass units times 1.00 atomic mass units. So we're talking about the individual nuclei here, divided by 35.0 atomic mass units plus 1.0 0 atomic mass units. And so that ends up being, well, we've got to convert this again. So 1.661 times 10 to the negative 27, and that's kilograms per atomic mass units. So what we're going to find is this will cancel, this will cancel, this will cancel with this, and so we'll be left with something in kilograms. And the answer here, plug and chug type question, 4.78 times 10 to the 2 kilograms per second, and that is equal to, remember we're looking for a force constant, 4.78 times 10 to the second newtons per meter. And remember, 1 Newton again is a unit of force, and F is equal to MA. So that would be mass would be kilograms meters per second squared. Okay, so and then we look at these units, we see the units we've already got, and that's how we end up getting the newtons per meter, and that's the units for our force constant. So very plug and chug there. We tend to, the point here is that we tend to work with wave numbers when we're working with spectroscopy, certainly in infrared spectroscopy. What else can we say about this, and how else is this important? Force constants for diatomic molecules tend to be around 10 to the second to 10 to the third, 10 to the 2 to 10 to the 3 newtons per meter. And we'll later talk a little bit more about spectroscopy. I'm going to plant another seed by saying here that we must end up seeing a change in dipole moment as the molecule vibrates. We'll talk about that in a later section when we think about an oscillating electric field and how that interacts with an oscillating dipole moment in a molecule. Those two things kind of have to connect with each other. So planting a seed again. So that's section 5.6. Section 5.7. The title is Overtones are explored in vibrational spectra. So let me try and set this up a little bit. I mentioned earlier how we have this Morse potential, and the Morse potential that we've seen looks something like this, and this is our potential energy here as a function of the separation distance. So this might be as a function of well, let's say internuclear separation. And this particular section of the textbook really talks about how there's a very close overlap with the Morse potential and the quadratic when the separation distance is small, or the value L is not much larger than the value L naught. So the stretching is very small, and we have a very good overlap. So in fact, let's see if I can draw this in red. But then what happens is we lose the overlap. Right, so this is basically saying that over this small region of X in here, okay, this is L naught, right? That over this small region of L values, we actually have very good overlap with the quadratic that we've just described. But in fact, what happens as we go to larger values of X and larger values of L, we need to have additional terms, and so the potential energy is described by a more complicated expression. So what section 5.7 does, I don't know that they do such a fantastic job here, but what we're going to recognize is that we can write a Taylor expansion about L naught, so about that equilibrium position in here. And what we get is the following expression. So let's change color. We end up getting V of L And by the way, series expansions are addressed in Math Chapter D. So there's the explanation, and I highly recommend that you take a look at that. So what we end up getting here, I'm going to write this down at the bottom. So here's a Taylor series expansion about L0. And we can already recognize a couple of things about this expression. So I'm going to say we're aided by first of all, x equals L minus L0, and therefore dx by dl is going to be equal to 1, and therefore we know that dx is equal to dl. So that's going to help us as we go from Math Chapter D in here, the Material Math Chapter D, to this series expansion. The second thing we're aided by is that at x equals 0, we recognize that L is equal to L0. Okay, so that's right at this position here, the equilibrium position. And lastly, we're going to say when x is small, we can neglect the further terms. So what does this tell us? How do we get there? Well, let's take a look, and then we'll come back to this slide. First of all, let's ask the question, how do we get this? So let me just give you a quick synopsis of Math Chapter D, where it pertains to this particular Taylor expansion. It'll take a few minutes, skim through it if you would like. And then what I'm going to do is actually going to replace some of these terms in here so that we can really end up simplifying this expression. So Math Chapter D, what that tells us is if we want to take a function and expand it and write it into a Taylor series, we can use these coefficients C0 plus C1x plus C2x squared plus C3x cubed plus C4x to the fourth, etc. Okay, and what we first do is, number one, we say let x equal 0. Okay, so of course in the first case, when we let x equals 0, we find that all these terms where there's an x in there go away, and so we recognize that f of 0 is equal to C0. The next thing we can do, so then we say, okay, df of x by dx, what happens if we take the first derivative of our whole series expansion, right? So if we take the first derivative of this, well, that ends up being equal to C0. Well, the C0 is a constant, so that goes away. So we end up with C1 plus 2C2x plus 3C3x squared, etc. At that point, we say let x equals 0. So when x is equal to 0, what we find is that, in fact, we're going to write it like this. So let x equals 0. We recognize that df of x, therefore, by dx at x equals 0 is simply equal to C1, right? Because all this stuff in here goes away when x is equal to 0. So when x is equal to 0, these terms disappear, and all we're left with is the C1 in here. Okay, so we end up having a new value for the constant C1 in our expression. We can keep going, right? So what we can do is we can say, okay, now we're going to take the second derivative of our function and take the second derivative of the whole function again. So this whole function, we take the second derivative of it. Let's change colors again. Second derivative is equal to, well, the C0 goes away, the C1x goes away. So what we're left with is C2 plus, what do we have now? We've got the first derivative, 3c3x squared, which becomes 6 c3x plus etc., etc. And the key again is to say, well, when we consider the second derivative at x is equal to 0, then all the rest of this stuff goes to 0. And what we're left with is simply the C2 term. So this value ends up being equal to C2. I'm sorry, ends up being equal to 2C2. Because our second derivative here becomes 2C2. Well, the first derivative is 2C2x, and then the second derivative ends up being 2C2. So that 2C2 there becomes the 2C2 that we see in this expression. So when we put that all together, right, what we find is we come up with one final expression, and that sort of generalized expression can be wrote as shown at the bottom here in black. F of x equals f of naught plus d f of x by dx at x equals 0. That is the coefficient, right? That's this C1 coefficient multiplied by x plus 1 over 2 factorial. This is the 2 factorial. We get the 2 factorial because of the sequential derivative taking. So this ends up being d squared f of x by dx squared, again at x is equal to 0, multiplied by x squared. And we keep going. 1 over 3 factorial we would get in here, and that would be d cubed f of x by dx cubed. That's at x is equal to 0, multiplied by x cubed. And we keep going. So this expression, this series expansion, what we can do is we go back and we recognize that is what we have got in this equation in here in the textbook, and that is equation 5.40. Why am I bringing this up? Okay, so what are we going to do with this particular expression? Let me rewrite it, and we can narrow it down a bit. Okay, here's the same exact structure that we've seen in that math chapter. And what we recognize now, as I said before, this value in here basically is 0. Okay, there is no potential. Really, we're saying the potential is 0 at the bottom of that equilibrium piece. So that's the potential at L0. We can arbitrarily say that that ends up being 0. And that sort of helps us. But most importantly here, what we're thinking about is the shape of this Morse potential. And we recognize that dV by dL at L equals L0, this expression here at equilibrium, right? This the turning point, the change in or the slope at this point is quite clearly equal to 0. And so this term effectively goes away. It turns out that this d squared v by dl squared term is simply equal to K. Okay, and it also turns out that this D, this is a cubed, D cubed V by dl cubed term, we're going to say is equal to some new constant. We're going to call that constant gamma sub 3. With additional terms, we might also get to a point when we're interested in the d to the 4, d4 v by dl to the 4, and that would be equal to gamma 4. But what this boils down to is an expression here that is v sub l minus, well, this is going to be 0 effectively, but it's arbitrary, so we'll keep it in here for now. And that's equal to, we'll put it as k over 2 times x squared. So remember, this x squared term is actually L minus L naught in here, so that's the x squared, plus 1 over 3 factorial, well, that's actually going to be 1 over 6, right? And then we've got this gamma 3 term in here, and then we've got the x cubed term, and we can keep going, right? So we're going to end up having 1 over 24, which is 4 factorial, gamma 4x to the 4. And so what's the point of this? There are these overtones. So as we get to larger values of x, we need to have these expressions that describe how the potential energy moves away from the quadratic expression. Why do we need this? This pops up in spectroscopy, so we start to see these overtones in spectroscopy. And that's really effectively what section 5.7 is telling us. Let me try and sum this up. So, when we keep x small, we can neglect the further terms beyond the quadratic. There are overtones in the spectrum. So we do see these. These are lines of weaker intensity. I'm going to plant another seed. I'm going to say that perturbation theory can be used to build and solve the Hamiltonian to include these additional harmonic terms. Okay, so what we have effectively here is still a classical description of the potential, and we can plug that into an ever more complicated Hamiltonian operator or Schrodinger equation and solve it. And when we do that, this actually gives us a solution as follows. And now this is a customary G-type solution, and we still use the same quantum numbers 0, 1, 2, etc. This is now what we call an anharmonicity constant, and it is very small. So here's our equal spacing, but what this actually means is that we start to see a deviation. We may have seen, for a simple quadratic, we would have seen this equal spacing, but now with this anharmonicity constant in here, what we find is that the actual there's a minus sign in here. Okay, so the minus sign, so this energy term in wave numbers gets smaller, gets lower than our final value. So we tend to see this offset in energy levels. So here's the G of V energy levels in here. and we'll say that the levels are spaced such that separation decreases with increasing v, and that's because of that minus sign. And it turns out, last point here is that for any for an anharmonic oscillator, this delta v can actually take any integral value. So delta v can be plus or minus 2, plus or minus 3, etc. Although those line intensities are very small. So for those anharmonic oscillators, we do have some oscillator strength, we call it, from say v equals 0 all the way up to v equals 2. So for an anharmonic oscillator, delta v can take any integral value. It can be delta v could be equal to plus or minus 2, 3, etc. But line intensities are small. Okay, I'm going to stop at that point. After all this, we're still really talking about the classical descriptions, and so we're kind of dancing around the idea of, well, we kind of need to think about what the actual wave function looks like. We've talked about eigenvalues. We've expanded our thoughts to consider spectroscopy in here, but next up, what we really need to do is start to think about the wave functions themselves, and that's what we'll do in the next section. Thanks for listening.